Okay, I think we're ready to start. No worries. Okay, thanks, man. Okay, good day, everyone. My name is Matt Quail.
I'm Brendan Humphreys, if you haven't met me.
And we're both senior developers from Atlassian.
And what you're looking at here on the big screen is a question that we use to interview technical candidates at Atlassian. What happens when you press submit on a web form? It's a seemingly innocuous question, but it's a good one because we like to see how technical candidates can get in answering it, how far they can drill into the layers and layers and layers of technology that are used to handle a web submission and processing and then the subsequent response. So your basic programmer will tell you about a few things. They'll tell you about a HTTP request, they'll tell you about a HTTP response, they'll maybe tell you a little bit of detail about what the server does. But a better candidate will maybe add a few more details. They might talk about TCP/IP, they might talk about DNS, they may talk about HTTP status codes, for example. What we're looking for is the exceptional candidate, and the exceptional candidate can paint an insanely elaborate picture of what goes on when you press a button. You hear all sorts of stories about mouse interrupts, system level calls, everything down to PN junctions and strange quarks. When you think about it, it kind of illuminates that we kind of take for granted the layers and layers and layers of technology that we sit on and use every day. And
well, and it's not even the best candidate, or not even the best candidate, knows all of this. In fact, no one in the world really knows, everything there is that goes on at the click of a button.
Except maybe this guy. I think he would probably know. He invented most of it, so.
That's right. So what we want to do today is to peel back just some of those layers and think about some of the incredible technology that we do take for granted. Now, we're software guys, but even so, it's easy to forget just how much software is involved in all these processes. So you just think about it in terms of lines of code, it really starts to add up. Operating systems got up to 80 million lines of code. A browser is 4 million lines of code. You've got your web server, a web container, your web app, and then even something like a hard disk itself has software running on it. The I/O controller has software on it. A CPU has microcode on it. Switches, routers, and modems have whole operating systems on it. So it quickly adds up to something like over 100 million lines of code involved in just clicking a button on a web page.
Now, when we were doing these slides, we thought 100 million lines, that's a pretty hard number to get your head around, especially if you're a developer, 100 million lines of code. So just to help you think about it, imagine you're an average developer, like this dude, and you can write about 200 lines of code a day. Do the math, you're not going to finish writing those 100 million lines of code until the year 3321. You try telling that to your project manager. And if you print out all this code, so you can read it in, say, 14-point Arial, you could use Comic Sans or whatever you want. You'd need about 2.5 million pages of paper. Now, if you would lay those pages end to end, they'd stretch further from here than from here to Los Angeles. And you'd use about 285 trees in the process.
It's like a forest.
It's kind of like a forest. It's actually, technically, it's a grove.
It's a grove? Isn't that?
If you look it up, it's actually a grove.
Okay.
And most of this software actually sits on your hard disk drive.
Now, I know, or you know this, but to most people, That's what's called the hard drive, but I know none of you think that. What I want to talk about for the moment is one of these, a hard drive. Now, you can look at your average 500 gig disk, they're pretty common, and think to yourself, yeah, okay, I suppose that is a lot of data, even though I can fill one up pretty quickly. But what we don't take into consideration is just the incredible speed and precision at which one of these guys run. So I've got a bit of an analogy. Imagine a hard disk that was as big as an Olympic-sized running track. Now, the current 100-metre sprint runner, a guy named Usain Bolt, he can run that 100 metres in like 9.69 seconds. Imagine he is running around that track. Now, bear with me. If he was to run as fast around the track as the hard disk is spinning, he would have to not double his world record speed, not quadruple his world record speed, not even increase his speed by a factor of 1,000. He would have to be running 4,000 times as fast as his record in order to be running around that track as fast as the hard disk spins. But wait, he's also holding a newspaper. Now, yeah, it's a newspaper, check it out and bear with me. Now, he's running around fast, he's holding a newspaper and you're standing on the sidelines. Each time he runs past, you have to read a clue from the crossword and write down the answer each time he runs past. That gives you an idea of the scale and precision at which a hard disk is operating. But it's even a little bit more complicated than that. That newspaper is just the size of a grain of rice. So he's running around his grain of rice.
It's just an awesome analogy. I'm sure you'll agree. I didn't approve of that one, but
impressive.
I personally would never think of hard disks the same way after Matt came up with that one. Anyway, so all this software actually runs on a CPU, and this is a picture of a modern CPU. And these guys are incredibly complex. In fact, orders of magnitude more complex than a hard disk drive. Now, the analogy I'd use here is if you imagine Usain Bolt is, no, I'm not going to go there actually. Give Usain a rest, he's been sprinting around a modern hard drive and blah, blah, blah. A modern CPU is about 1 billion transistors. 1 billion transistors. That's a lot of bloody transistors. Again, it's a hard number to think about. So what I wanted to do is create an impression of the scale of a modern CPU by trying to build one out of 1940s technology. Now, this is the 1940s equivalent of a transistor. This is a vacuum tube. Now, it stood about 5 centimeters high, they're about 3 centimeters wide, they consume about 8 watts. If you could assemble 1 billion of these, you'd have the power of a modern laptop CPU. Except you'd need a bloody big place to build it. In fact, you'd need 6 times the floor area of the Pentagon just to house all the valves. And you'd want to think pretty carefully before turning it on, because when you did, it would consume about 3% of total US power consumption just to power up. Put that in perspective, that's about 7 times the total energy used in the space shuttle launch. You can thank Wolfram Alpha for all these amazing comparisons, because they... But it turns out you couldn't build one realistically because you would exhaust the world's copper supply just trying to build the interconnects between all the valves. But let's just say, for the sake of a really, really tortured analogy, that you could overcome that.
That's the drawn-out analogy.
That you could overcome that and you actually got the device working and you wanted to do something useful on it, like listen to your favorite MP3 file. You would wait about 250 years for the MP3 to decode, which in this case wouldn't be a bad thing because Rick Astley will still be very much in fashion in 250 years.
Never, ever, ever.
So we kind of got a little bit lost in answering our own question of what actually happens when you submit with our awesome analogies. It does seem like a seemingly easy question, but it's great because it does illuminate so many levels and abstractions that we take for granted. And to give you an idea of that, I'm going to put Matt kind of on the spot, except he's done it before and we rehearsed it.
I'll pretend like I'm giving an answer off the top of my head.
To have a go at actually answering this question. Take it away, Matt.
Okay, so
your job may be on the line.
Yep. Okay, so what I want to do is just try and give a quick answer to this question just by thinking about the data representations involved. So not any of the computations, just how data moves throughout answering this question. So you're looking at a browser, and on the screen there is a button. Now that screen on the browser is generated from a HTML representation of that page, and there's a little form in there with a submit button and some input fields, and you click that submit button, and the browser gets all those input details and puts them in a form, in some post data, and that post data is wrapped in a HTTP request with a body and a header, and that gets sent down a TCP stream. That TCP stream is just not a big long string of data. It's broken up into little packets. Each little packet has its own little header and a little parity bit, and they go down a wire. They eventually get to the other side after a whole other series of little breaking up over trunk lines and things like that. Eventually get to a server. A server will take that data, have a look at the headers, strip out the body, put those body maybe in a representation for the web app to consume, like a hash map or something like that. And then your web app goes and processes some information, collects some data from a database. It may have internal object model representation of that data that eventually then gets spit out as HTML. You've got the same sort of TCP IP thing going on. And then eventually it all comes back to the browser as HTML, and then the browser looks at that data that represents that HTML and shows you back something in the browser.
All right, that's awesome, Matt. I think Matt can keep his job. He's pretty safe there. But Matt, of course, just focused on the data transformations that are going on there. And again, it's the computation that's involved at every step of the way, and certainly on the server, is insanely more complicated. Now, I'm not going to try and match Matt and tell you about those the data transformations and the computations that are going on. But what we are going to leave you with is just the amount of work that your computer is doing when it receives a page of HTML and wants to render it for you to see. And so I've got a little video here of what actually happens. Now, the monitor's not so good. But what we're looking at here is what's called reflow, or the reflow algorithm that recursively renders HTML in the browser. And this is seriously a stock standard HTML page. And this is slowed down, I think, I don't know.
A couple of orders of magnitude, yeah.
At least a couple of orders of magnitude. I think this, and there you have it, mozilla.org. All that work is probably done in real time in about 5 to 10 milliseconds. So we hope with our tortured analogies, we've kind of illuminated that in today's world where we want everything at the click of a button, some of the things that actually happen when you click a button. Thank you very much.
Thank you.
We'll be here all week.
Try the steak.
Are there any questions? If you want questions on how to use Keynote to, anyway. No.
Where are the what? They're everywhere. Where's open reason?